Today, we're going to talk about a problem that used to be a massive headache for electrical engineers. And the really cool part is how they solved it. It wasn't with some new piece of hardware, but with a piece of pure, beautiful mathematics.
So think about our entire electrical grid. I mean, everything from the giant power plants to the little outlet in your wall. It all runs on alternating current, or AC. And that word, alternating, is the key. It means the voltages and currents aren't just sitting still. They're constantly changing, which makes trying to analyze them, well, a real challenge.
So how do you even begin to wrap your head around a system that's always in motion? Let's jump in and unravel this thing because the solution is one of the most elegant ideas in all of engineering, and it literally powers our entire world.
Right, so in an AC circuit, the electricity isn't just flowing in one steady direction. It oscillates. It's constantly rising and falling in this smooth, predictable, wave-like pattern. We call this a sinusoidal signal, and it's basically the fundamental language of all things AC.
Now, when you try to work with these waves directly, you're in what engineers call the time domain. And let me tell you, doing math here is a total nightmare. Imagine trying to add two of these waves together. You have to worry about their height, how fast they're oscillating, and if they're even in sync with each other. It's all calculus, specifically differential equations, and it makes designing even a basic circuit an incredibly slow and painful process.
So engineers were desperate for a shortcut, a way to just sidestep all that messy calculus. And the answer, amazingly, didn't come from an engineering lab. It came from the world of pure math, with a formula so beautiful and powerful that it got a pretty amazing nickname, the Joule.
That's a quote from the legendary physicist Richard Feynman. And he was talking about this one surprisingly simple equation that acts like a bridge, connecting two parts of math that on the surface look completely unrelated, the world of waves and the world of exponents. And here it is. This is Euler's formula. This is the magic key that unlocks the whole puzzle. What it does is it gives us a way to take those two messy, wavy functions, sine and cosine, and wrap them both up into a single, much cleaner exponential expression. This one move changes everything.
Okay, so a beautiful formula is great, but how does it actually become a tool that engineers can use? Well, this mathematical Joule gives birth to a concept that is absolutely fundamental to AC circuits, something called the phasor.
The easiest way to think of a phasor is as a snapshot of a wave. Instead of wrestling with a signal that's constantly moving, the phasor just freezes it. It turns that whole complicated wave into a simple little arrow, a vector. And that one arrow tells you everything you need. Its length tells you the wave's peak value, its amplitude, and the direction it's pointing tells you its position in the cycle, its phase.
Now here's where it gets really clever. We can describe this little arrow in two different ways. Think of it like giving directions. Rectangular form is like saying, go 4 blocks east, then 3 blocks north. Polar form is like saying, go 5 blocks in a northeasterly direction. They both get you to the exact same spot, but each method has its own mathematical superpower.
So why would you bother with two different notations? Because this is the secret. This is how we get to throw out all that hard calculus. By being able to switch between these two forms, we can replace those difficult differential equations with simple arithmetic. You know, the stuff we all learned back in grade school. For instance, if you need to add two signals together, which happens all the time, the rectangular form is your best friend. You just add the horizontal parts together, and then you add the vertical parts together. It's really that simple.
But what if you need to multiply or divide? That's super common too when you're dealing with something called impedance, which is basically just the AC version of resistance. Well, for that, polar form is way easier. You just multiply the lengths of the arrows and then you add their angles. Again, no calculus anywhere. So we have this really elegant mathematical trick, but how does it connect to actual hardware, to real circuit components? This is where the big aha moment really happens. Just take a look at this. On the left side, in the messy time domain, you see the equations for inductors and capacitors have those di/dt terms. That's calculus. That's the hard part. But now look at the right side, in the phasor domain. All that calculus has just vanished. It's been replaced by these simple algebraic terms we call impedance, which we write with the letter Z.
And because we've magically simplified everything down to these simple impedance values, we can now use a supercharged version of the most famous law in all of electronics, Ohm's law. Voltage equals current times impedance. We just successfully turned a really difficult calculus problem into a simple algebra problem. That is the power of phasors.
So let's just zoom out for a second and appreciate what just happened here. We started with this super complex, wavy problem that was a real pain to solve. And we found the key to unlocking it, not in some fancy modern lab, but in a beautiful mathematical formula from the 1700s.
And this whole transformation from the time domain to the phasor domain, it's not just some cute little academic trick. It is the fundamental technique that makes modern electrical engineering work. Without this, designing our power grids, our computers, our smartphones, literally anything that uses an AC signal would be unbelievably harder, maybe even impossible.
It's just an amazing reminder that sometimes the most practical, world-changing solutions don't come from just trying harder, but from finding a new way to look at the problem. From finding these abstract and beautiful ideas. It really makes you wonder, right? What other jewels of knowledge are just sitting out there, waiting for us to find them and solve the next big challenge?